Okay, so the next section is controlling program flow. Computers typically execute instructions in linear order in a sequence going through main memory. But we are allowed to change the flow of control using several instructions. There are two general ways, the jump instructions and the call instruction. We'll do the call instruction in a couple of lectures. We'll cover the jump instructions here. In terms of jump instructions, there are two kinds. There are the unconditional ones. These are like your go-to statements. No matter what, you jump. So you can say jump to a label. This is a direct jump, assuming that you know the address at compile time where you're going to jump to. There's also this indirect jump. If you're going to calculate your jump target at runtime, then you could do this jump star operand. And you'll see a case of this in one of your binaries where it's doing an indirect jump. And the problem with an indirect jump is that if an adversary can corrupt this operand, then it can make that program jump to a place that it didn't want to jump. And that's basically what one of the last binaries in Chapter 8 is going to have you do. Okay. The other kind of jump is the conditional jump. And this is a jump only if a certain condition holds. And so in your loops, in your if-then-else statements, that's where your conditional jumps will occur. So anytime you have control flow constructs like this, so the if-then-else, the while loop, the do-while loop, and the for loop, as well as the switch statement. Well, the switch statement less so, but definitely these three. This is where you'll have conditional statements. You'll be checking conditions and then conditionally branching to one place or the other based on whether that condition holds. The way this is implemented is using this processor flag register called E-flags. And when if we go back all the way to the beginning, the assembler level's view of the computer, there was the CPU that had registers and E-flags, that was the other processor state, and then your memory. So this is the E-flag part of it. The main condition codes that we're going to look at are the carry flag, the zero flag, the sign flag, and the overflow flag. And these bits are set or cleared based on the previous operation. So if you did a subtraction and the result was 0, well then this 0 flag will be set. If you did a subtraction and then the sign bit was set, and it was a negative, then this sign flag will be set. So you could actually test that most significant bit manually, or you just look at the sign flag in this E-flags register. Here are some examples of the bit being set implicitly. So every arithmetic operation and every logical operation will set these flag bits, these 4 flag bits. So if you have this instruction, add source to destination, where the result is t, then the carry flag is set if a plus b leads to a carry out of the most significant bit. This is your unsigned overflow, right? And we saw this in the exam. When you have 2 5-bit numbers and you overflow that 6-bit, well, it gets lost. But you have to make sure you check for that, right? You want to know if that thing has overflowed. This is what the overflow flag allows you to do. Check for that. The 0 flag is set if you adding these two things results in the destination being set to 0. If the sign flag is set, that means the most significant bit. This is for signed integers. That most significant bit is 1. Yeah.
With the carrying out the most significant bit with the addition, does that happen to any amount of bits that are overflow, or is it only
any?
Bits?
Oh well, it turns out it's only there's only one bit that can overflow because you have 2 n-bit numbers. You can only overflow into n plus 1.
Yeah. Well, so if you wrap back around, will it set it back to null?
So this is specific to the addition that just happened.
Yeah. So if you add through, it gets set, and then I'm assuming it just continues adding correctly?
After you execute this instruction, then you have another instruction potentially, and then that will set the flag registers differently. Yeah. There was a question over here. No? So the sign flag, and so the different flags, you're not going to pay attention to all the flags every single instruction. If you're doing unsigned arithmetic, then the flags that you care about are the carry flag and the 0 flag. If you're doing signed arithmetic, then it turns out you're only interested in the sign bit and the overflow bit, which tells you 2's complement overflow. So here is unsigned overflow is implemented with the carry flag, and then the signed overflow is basically this overflow flag, and that's why that's there. For you to be able to detect these overflow conditions, and then to use those in your conditional branching as part of the conditional branching. Okay. More often than not, you will explicitly set these condition codes using a compare instruction. So when you see an if loop or an if statement or a while statement and you see the thing in parentheses, typically that thing in parentheses is being evaluated using either a compare instruction or a test instruction. And the semantics of the compare instruction, if you have compare quad b comma a, this computes a minus b without setting the destination. All you're doing is getting the flag registers out of that subtraction. And that's typical in the if clause, where you're saying if x is greater than y, or if x minus y is greater than 0, these sorts of things. You're not actually setting x or y to be anything. You're just doing the subtraction and looking for what gets set in the control flag register. So in this case, the carry flag is set if a minus b leads to a carry out on the most significant bit. The 0 flag is set if a and b are the same, so you're checking if a is equal to b. So it turns out if you do an if a is equal to b, you'll see it'll turn into this instruction, followed by a conditional branch based on the 0 flag. And we'll see an example of this. The sign flag is set if a minus b is less than 0, using 2's complement arithmetic. That most significant bit is set. And the overflow flag is set if you have this 2's complement signed overflow. So if you have a is greater than 0 and b is less than 0, and it turns out a minus b is less than 0, this indicates overflow, right? You have a positive number, you subtract a negative number from it, it should be a positive number. But if it turns out it's negative, that means you've got an overflow. Likewise, on the other end, if a is less than 0, b is greater than 0, and you have a minus b be positive, that means you have overflow on the other end. Those are the two cases of 2's complement overflows. And these are the things that you're checking in your conditional branches to make sure you get the right conditions set. Similar to compare, there's also this test instruction. And test and compare are the same, except instead of a minus b, you do a bitwise ANDed with b. And this is typically done in networking code where you're masking off bits and checking to see, if you have certain prefixes set. So this is not going to be used much, so I'm going to just skip on by. But it's got the same sort of semantics for these fields. Okay, so now we have those bits. Now we're going to have a whole bunch of conditional branches based on what these bits are set to from the previous compare. So I'm going to cover a couple of these. So this is unconditional jump. The jump equal or the jump 0 says if the previous instruction resulted in a 0 result, then take that branch. The jump not 0 or not equal says take the branch if the result isn't 0. So you take the bitwise complement of the 0 flag and you jump based on that. So jump equal, jump not equal, those are implemented with these two. Similarly, you have the sign flag and the complement of the sign flag for negative and non-negative. Greater than or equal to, you're basically looking for the sign flag but not the overflow flag. And these aren't obvious, but these are basically making sure that you not only look at the sign flag, but whether or not the overflow flag also got set. Because if you have both an overflow condition and a sign condition, you have to handle that overflow case. So, but I'll skip those and go to an example. So here is an example of it using some C code. So absolute difference, you're taking the absolute value of x minus y. So if x is greater than y, then return as the result x minus y in blue. Otherwise, you return y minus x. So this is your C code, and you compile this using these flags, and you get this as your assembly. And so I'm going to step through this assembly. So when you call into this function, the parameters x and y are in RSI or RDI and RSI. So x is in RDI, y is in RSI. And so this compare quad does an x minus y. And if you get the jump less than or equal to, that means that this turns into a negative number. So if x is less than or equal to y, you're going to jump to L4, which is this thing on the bottom. So I've labeled this here as x being less than or equal to y. And if you look at the code that is there, you're going to move RSI, which is y, into REX, and then you're subtracting x from it. So this is calculating y minus x, which is exactly what we have here. All right. The other one takes RDI, which is x, moves it into REX, and then subtracts y from it. This is exactly what's here. And then both of them will return, leaving the result in REX, which is where we have left those two results. So take a look at that. Does that make sense to you? How this if then else gets implemented using this compare instruction with a conditional branch. Okay. So this is the general pattern. So you have this value, you're having a test condition, and you're either executing the then or the else. So for example, if x is greater than y, return x minus y. Otherwise, return y minus x. This is the C code. And the version that implements that in assembly is you're checking if the negative of the test condition. So the test condition was x greater than y. If you look at this, you're actually testing x less than or equal to y, the opposite. And so that will end up down here. And so this is the code pattern of the if then else. You're actually going to test the opposite and then jump to the else. And then the fall through is to calculate the then expression. So when you go and reverse engineer code, keep that in mind. So I'm going to have you, in fact, I think I have this is the practice problem 318, which is what I want you to work on. And keep in mind, when you see greater than or equal to, that this is testing less than in the if statement, and then the fall through is the then clause of this. So I want you to work through this, and this is going to be really hard, so I would imagine if you guys collaborate as much as possible and double check what each of you have, that would make this less painful. So this is a leap, and I'm going to give you some time to do this. So yeah, let me at least give you the first two. So the first thing is you see this val gets initialized, and this is the thing that you're returning. So look for that in REX. And so that's what this is. If you see LEA quad RDI RSI into REX, that's adding x plus y into REX. So this is your x, y, and z are your parameters. X is in RDI, y is in RSI, z is in RDX. So this adds x and y, puts it in REX. And then it adds RDX, which is z, into REX. So this is basically saying x plus y plus z is what's in val. And then the first compare, followed by the conditional branch, you're comparing x with -3. So this actually does x minus -3, but you're basically comparing x with -3. And then if x is greater than or equal to -3, you're jumping to this. So that's the opposite of the test that you want. So this is checking if x is less than -3. So from that pattern in the previous slide. That's the one that's confusing. But based on this, then you, in the then clause, the fall through is implemented right below. And you see the fall through gives you another compare, and I forgot to put the quad in there, another compare with another conditional branch. That will allow you to calculate this if clause and then work from there. So I'll pause here so that you have at least that to work on. All right, let me just give this to you incrementally. Hopefully you were able to get some practice working these out. We left off here where we found that this was x is less than -3 because it's testing the opposite condition. And then this is branching to L2. So that means this L2 clause is this else part of this if then else. So we'll get to this later, but that's what this will be at the bottom. The fall through of this is another compare. And that's basically going to implement this if statement. And you're going to compare RSI to RDX. So RSI is Y, RDX or RDX is Z. Sorry. So you're comparing Y to Z, and you're jumping if Y is greater than or equal to Z to L3. But the fall through is the opposite. So in this case, the condition for the then is Y is less than Z. Right? So it was greater than or equal to, you're jumping. So that means when Y is less than Z, you're over here. Yes? Okay. Okay. All right. All right. So then, finally, you get some instructions that aren't conditionals. So this is the fall through, right? So move quad RDI. This is moving X into RAX, and then you're multiplying RSI into RAX. So this is taking X times Y and setting val to it. And then you're returning, right? Because this is what val returns it with. So you return, you could either put return here, and well, there's no parentheses here, so it goes right through. But yeah, it's basically going to return directly. Okay, so let's then resolve this inner if statement. So the Y is less than Z. If Y is greater than or equal to Z, you jump to this L3. And that's going to implement this part. And here you're going to move RSI, which is Y, into RAX. And then you're going to multiply RDX, which is Z. So this is taking Y times Z, setting it to val, and then returning it. Now we can resolve the else at the bottom. So we're going to compare RDI, which is X, to 2. And if X is less than or equal to 2, we're going to return, basically, jump to L4. If X is greater than 2, then we're going to go through this fall through. So the fall through, so if X is greater than 2, we're going to go through this fall through, otherwise we're going to return. And this fall through is RDI gets loaded into RAX, which is X, and then you're multiplying RDX, which is Z, so you get X times Z. Yeah.
Is val in RAX?
Yeah, so the thing that always ends up in RAX is val, and so that's what the compiler, that's why the compiler is using RAX on all of these things, because it knows that it needs to leave that result in RAX when it does this return val. That's how you can map the two. Yeah.
If you had return statements instead of setting vals, the things in there, would it still come up with very similar code?
Yes. If you put the return right in here instead of having it fall through, yeah, same.
The returns after L3 and
That one?
yeah, and the one above that.
Yep.
Those are after those. L3 is that last, the second is the only else statement, right? Right. So returns after you set the value.
Yeah, so this return and this return are for after you set that value and after you set that value. And it would basically, it's your way of breaking out of this if statement.
Right.
Yeah.
I thought the second if statement would be x less than 2 because that first if x is less than -3 would only execute to the second one if you jump to L2. But I guess I'm wrong.
This is the semantics of the conditional jump is that you will jump if that condition holds. Otherwise, you keep on executing.
So if x is less than -3, then it would go to L2.
It would go to this right here. No. So you test the opposite condition. So we tested for x greater than or equal to -3. And then we jumped to the else. So that was the trick about checking for the opposite and then jumping. Because, that way the code that's here on the left structurally is the same as this one. And so in order to do that, you conditionally branch on the opposite to get to the else part. And then the positive condition falls through. That's the tricky part of the if then else. Yeah. All right, so
Is the calling code supposed to just know to look at REX for you?
yes, so this is a calling convention that has been established by the compiler, so that if the compiler, so for example, you're using libc, and you're calling libc functions and using the return values from the libc functions, well, there has to be a calling convention that said, well, where do I look for the return value from a libc call? That's this. So there's a contract that gets established by the compiler with all the code that it compiles that says, this is how I am taking my parameters in, this is how I'm returning values back out of the function, and it's all a compiler convention. Yeah.
You're telling us what values are in which registers. How would you find that out?
In 2 lectures, it's again calling convention. It's just standardized this way, and you see that this calling convention specific to x86 64 for the architecture that we're using here. In previous iterations of this class, I taught a different calling convention that pushed all of these parameters onto the stack in memory, and then you have to go into memory to find your parameters. So that was IA32. It pushed it all on the stack, and then you would have to, in the debugger, you'd have to go into memory to figure out where your parameters are. And then the caller, in order to call the function, had to set up the stack, push all the parameters it needed onto the stack, and then issue the call. Here, the caller just says, well, I just put them in these registers and then issue the call. So this is faster. This is why they went to this, because the previous way, that's a lot of memory writes. Yeah, that's a lot of memory overhead. And it turns out memory is the bottleneck, the number one. Now it is. Before it wasn't, which is why sending it on the stack was no problem. The memory's not a problem in 1980. It was one cycle for a memory operation, one cycle for a CPU operation. It was equivalent. So it was yeah, you just stick it in memory. But now they're completely different. So they had to change the calling convention to say, forget it, we're not going to touch memory. We need it in the registers. That's what this is doing. That's one of the big reasons why this change was made. Yes.
It's one of the other things is the increase to having more registers means that the function calls are more efficient because you're not having to completely redo the stack every single time.
Yes. So function calls are more efficient this way. With this calling convention, that's correct. Yeah. And I know some people were like, "Oh, I'm trying to avoid function calls in my assignment 1."
Yeah.
And I realized that is it's different kinds of optimization, but we actually would prefer for this kind of a program that you stay modular and readable, because it's not a high overhead it's not a high performance situation. But when you get into really high performance computing and you're like, I don't want that function call. Can I inline the function? And that's what a macro will do. It'll just do a string substitution. You have something that's a pound define that's actually a function. And then you say, let the preprocessor just paste that function in its entirety, so I don't have to actually do a real function call. That's what you'll get to that, and when you go to a high performance computing environment and you don't want to issue calls to functions, that's what you'll do. But it's these trade-offs of maintainability, readability, portability, versus just raw outright speed. So yeah, you don't want a function call inside your inner loop. of a scientific computation. That would be poor form, is the idea. Okay, so the next thing I want to talk about, we talk about conditional branches, and now we talk about why conditional branches are terrible. They're really bad for performance. And so one of the issues is that because memory is so slow now, you have to fetch instructions well in advance. Otherwise, you're sitting there waiting for that thing to execute. So the CPU is trying to fetch multiple instructions ahead of time before it even gets a chance to execute them. As soon as it hits this conditional branch, it's like, well, what instruction do I fetch after that conditional branch? The then? The else? I have no idea. I could either stall the pipeline and wait for that condition to resolve and then start fetching instruction, or I can guess. I can just say, I'm guessing then this time, or I'm guessing else. I'm flipping a coin. So that's why conditional branches are bad. One of the things that Intel did in the sort of the Pentium Pro sort of range of CPUs, it invested heavily in branch prediction. So, for example, if you have a loop, and that loop is sort of like you go through that loop like 100 or 200 times, it's going to be like, oh well, the last time you predicted the positive condition, I'm just going to go with that, and I'm going to have these counters that try and predict which branch you're going to take, and I'm going to speculatively execute that branch is going to be taken, and then if I'm wrong, I'm going to completely undo everything. So that was the name of the game during that range of processors. That's incredibly expensive. A branch misprediction was incredibly expensive because you had to undo all the register operations that you predicted, that you speculatively executed. But that's what was going on. But there's other ways of addressing this issue. So you had a.
Isn't that like against the whole idea of like a Turing machine? A Turing machine can't tell when something's going to stop or what the outcome of the comparison will be before you have the values.
Yeah, it's just assuming, and then eventually it'll either be proven right or wrong within X number of instructions. Usually like 3 or 4 instructions. Okay. It will know that prediction was correct or incorrect, and then it would have to undo 3 or 4 instructions worth of work. Yeah. Yes.
Really modern like CPUs and stuff like that, they're actually taking artificial intelligence and neural networks, and then they're running them on billions and billions of programs over and over again to get like these really, really advanced good guessing, and then they're taking that and embedding that into the hardware itself by manually coding that exact representation of the artificial neural network in logic gates. Yeah, well, maybe. I don't know enough about Intel design. I've got to read your paper on that too. It's not like but they're starting to do that kind of thing.
Yeah, so what they're doing is they're logging all the addresses where they're conditional branches, and then based on that address, they're logging every single branch that it was either taken or not taken, and they're using that as a predictor in the old days. Yeah. So I don't know what they're doing now, but in the old days, that's what they would do. They would keep all this extra state based on every single conditional in your program, and then it was actually quite good. These heuristics were quite good at determining the branches, but still, the point of the slide was that branches are a pain in the neck. So, and I'm going to show you different instructions. I'll show you one instruction for getting rid of the conditional branching. There are a whole slew of instructions in the Intel Core sort of range of processors that are there to just avoid branches. And so I am going to talk about conditional moves, which are a way of taking that conditional execution and moving it into the data unit. So what does that mean? Here is an example of a conditional move that returns the maximum of 2 variables, x and y, where x is stored in RDI and y is stored in RSI. And so the conditional move instruction, like a conditional branch, can be used on any number of those conditions. It's equal to, not equal to, greater than, less than. It can be used on any of those conditions that you saw earlier with the conditional jump. But the semantics is I am going to conditionally move the source to the destination only if this condition holds. And what this is doing is, rather than conditionally branching, if you just do this conditional move, there is no branch, right? You just keep on executing down through the conditional move, and the result of the conditional execution is showing up in your data. Yeah, you guys see that? No.
Does that only happen on a ternary if? Or other such inline statements like that? Or?
Yes. Yes.
That's why they're cool.
So the condition is handled in the data unit. So this avoids stalling the control unit with that conditional branch, because the control unit can see this and be like, I'm going to fetch the instruction right after it and be 100% sure that that thing's going to get executed. So it can continue to prefetch these instructions all the way down because it doesn't have a blocker here. Okay. So here's an example for max of x and y. You move x, so x is an RDI, you move x into RDX, you move y into RAX, and you assume y is the answer. You're like, okay, I'm going to assume y is bigger, and I'm going to stick it into RAX. Here comes the compare. I'm going to actually compare x to y, I'm going to compare y to x. And if y is less than x, I'm going to move x into RAX. You see how that magic works. I'm going to check my condition, and I'm only going to move if y is less than x, because then x should be the answer of the max. So 3 instructions without an if then else, because typically you would have that conditional that we saw earlier. If x is greater than y, return x, otherwise return y, that sort of thing. Yeah.
And Google has been using they used to use just-in-time compilation on the Android operating system, and then they switched to a hybrid of just-in-time compilation and ahead-of-time compilation to be able to modify stuff like that. So for instance, if you have a max x and y, and the compiler at first assumes that y is always bigger, but 90% of the time x is bigger, after you use the program for a while, the compiler will figure out, okay, x is always bigger, and flip that.
Huh. I'd have to see that. That sort of seems a little aggressive to me.
So they'll recompile in the background. By just not really compiling, it'll do just-in-time compilation, and it'll figure out, okay, which one of these branches always gets
So, okay, so there are some fake conditionals. So it might be doing this. So we do this in malware a lot, where we pretend there's a conditional, but it actually isn't. It's sort of like doing XOR quad RAX to REX, and then doing a jump equal. You're like, well, dude, that always hits. Why are you doing a conditional branch? Turns out, if you're trying to confuse someone, like a reverse engineer, you would do a whole bunch of these things, and then so maybe your compiler's like, dude, that's always going to be. I am smart enough to know that that condition is not a conditional, and then I'll make that a unconditional. So that might be what they're doing. But one of the things with compilers, the compiler can never change the correctness of a program.
Yeah.
So it has to know that that's an invariant before it can optimize that out. So.
Well, it's not that it would optimize it out. It would just move it around. So it would
do the one versus the other. So let's get to, and this is not the instruction for that. This actually is going to force you to execute both branches, which is what the next slide is. But one of the things is the performance of this is 14 cycles, all in the data path, and a single control flow path. This is way better than that conditional branching implementation, which is why I'm covering it. Okay, but the overhead is that both branches are evaluated. So you're going to get X and you're going to get Y stored, and then you're going to do this conditional move. Just like we had a design pattern for the conditional branches, we have the same design pattern for the conditional move. So you have the result that's set to the then expression, and you set the eval to the else expression, and then based on the not test, you will overwrite the result with the else expression if the opposite condition holds, and then you return the result. So same construct as the previous one. So this is the branch version. If it's not test, you go to else. If not test, you use the else expression to assign result to. Okay, so here's an example of it using the absolute difference function that we saw earlier. So x and y are the parameters. So that's an RDI and RSI. So I have it in blue. So this is the then part is in blue. The red part is the else. So here, RDI goes into RAX, and then RAX now holds x minus y. So this is x and this is y. This gets x, and then you subtract y from it. So this result is x minus y. That's stored in RAX. And then in RDX, you calculate the else clause. So you move y into RDX, and then you subtract x from it. So this is eval is equal to y minus x. And then you do a compare. You see if y is less than or equal to x. And if it is, then that's where you conditionally move the one on top of the other. So in this case, you can see clearly you're doing both the blue and the red branches. You're calculating both in RAX and RDX. And then your conditional move after the comparison is just going to either go with one branch or the other. Okay. I am going to skip this. But this is similar to what the other example is. So just go through and work through this similarly. So you cannot use the conditional move everywhere. You can't just erase all of your conditional branches.
That's what I was thinking.
Yeah.
How you do that now?
So there are specific cases where the compiler cannot touch the conditional branch. The first thing is if you saw the absolute difference, it's calculating both branches. Well, what happens if both the then branch and the else branch are computationally difficult, right? Then calculating both branches just to avoid the if-then, the conditional branch, well, that's going to cost you. In fact, if either one of these is more than like maybe a dozen cycles difference, then you're like, well, why am I doing this optimization to begin with? And this is what the compiler has to know, right? When it chooses, it's going to choose one implementation versus the other. If it looks at the cycle times of these two and they add up to something more than what the conditional branch penalty is, it won't do it. So that's one of the things. The other thing is if the then and the else branches have side effects. So if you're going into memory and changing variables based on the condition, well then executing both branches is going to change the correctness of your program because they have side effects that impact each other. So again, that you can't do. Or stuff like, for example, that null pointer check, right? The whole reason you have that conditional check is to not execute one branch, right? Because then you get a seg fault. So you don't want to optimize that away, do you? Yes.
So as long as we're using like an optimizer flag in our compiler, it's doing all this for us.
It would do it for you.
Like I don't have to write my if-else statements differently or using assembly code.
Right,
to
right.
do this thing.
But this is to give you an idea of like, yeah, that compiler is taking what it knows about the CPU. And so this is specific to x86 64. And so it's saying, oh, I have this facility, so let me see if I can generate code that gives me the best implementation. So when you take CS201, you talk about compilers and programming languages. This is the kind of stuff that, yeah, the compiler writer has to take care of. So
How long does it take to write a compiler? Like, how do you make a compiler?
that's a good question.
How can you imagine a compiler? I've never seen a code of compiler. So how can you imagine it?
You can write. So if you have a well-defined language, and so this is sort of the reason why you take finite automata and context-free grammars. If you have a well-defined language, then you can write a parser first, and then you like a parser for C, and you can sort of see when you have a parser for C how natural this is, like a thin layer over assembly. You can sort of see now how some of this code gets generated, translated. So like a rudimentary compiler is probably within your grasp. I mean, assuming that you have someone else's parsing code. Like, I wouldn't be able to parse that. I wouldn't want to write a parser myself, but there are tools that help you parse languages, and then you would generate code based on the sort of the data structure. Similar to like HTML, have a parser that parses the DOM, and then based on that you can operate on the page.
Just always think how smart those people who create all these rules and in the background.
One day it could be you. Yes.
I don't think so.
Yeah, I'm not a compiler writer, but yeah, if this is the kind of stuff that interests you, I'm sure any of you could eventually be a compiler writer. It's just a matter of having the interest. In the discipline. Yeah. Take 320 and let me know. My compiler's course was very hard on me, so I'm not a compiler person. How much time do I have? I should at least be able to do loops. All right. I'm going to do loops. So loops are similar to if-then-else's. They're just basically implemented as conditional branches that go branching back onto themselves. So typically compilers like to implement loops as a do-while. Do this body of statements, and then based on an expression, you conditionally branch. So here's an example of calculating factorial using a do loop. So this is the C code. You set the result to 1, and then do result is equal to result times x, and then subtract 1, and then check to make sure x is still greater than 1, return the result. So in assembly, and this is very similar to the C code, move quad 1 into RAX. So you're going to use RAX for result because that's what gets returned. And then you're going to do the imul quad, RDI, onto RAX. And of course, you have to use the imul quad here because there's no constant that you're multiplying. So you can't use the LEA quad trick or the shift trick. That's an arbitrary integer in there in RDI and in RAX. So you have to basically take RAX and multiply x to RAX, subtract 1 from x, compare x to 1, and if x is greater than 1, you jump back to L2. Okay. And then all of these examples, so this is the C code, and if you do a GCC-S, this is basically what you'll get in assembly. And I have all of those in this directory if you want to go and look at the assembly code by yourself. So question, are these two pieces of code equivalent? So this is the do while, and then this is another construct that does the while do. If it depends, then the answer is no. So one no.
No.
Another no. Yeah, this is correct. This is a no. If you compile both of these things, you get this, what we saw before, but in the while do, you see after you initialize result to 1, you jump unconditionally to L2, and L2 will check the condition, and then conditionally branch back up to L3 in this loop.
So technically, do while is more efficient?
Do while avoids this initial branch, but it changes the validity. It changes the function of that thing. Because here, you're always executing this. Here, you only execute this if x is greater than 1. So they're actually functionally different. So if you have written this, the compiler will definitely give you this. Yeah.
Like, say if you had, on the other slide, if you had all like constant things and none of the values would be mutated, then the compiler will be able to optimize out that first branch because it wouldn't care because you're not actually changing any of the variables.
Yeah, if it can figure out that the thing that you're passing it is a constant, it would. Typically, compilers don't optimize into functions or between functions. They can only do that analysis within the function itself.
Yeah.
And we'll talk about this when we talk about, in Chapter 5, we'll talk about what the compiler can and can't do.
So I was wondering the purpose of the do while loop was. I was like, why? Why would I ever use this do while? Whiles work just fine.
Yeah, well, that's an extra branch.
Yeah, and now I know.
Yeah. Okay, so here's a factorial done as a for loop. And if you recall, what the for loop has an initialization, a test, and an update, and then your body. So this is the exact same code from result equal to 1, as long as x is greater than 1, and then you subtract 1 on the update, and then you accumulate x into result. So init, test, update. Do you think this code is equivalent to the do while or the while do? While do. So the semantics of a for loop is to check the condition on entry, and that's similar to the while do, where you're checking the condition on entry. And if you compile both of these, they will generate the exact same assembly code. And you'll see this in the, if you go to this directory and you actually compile it from scratch, you'll see that it's the exact same thing. Okay. All right, so I think I can, let me see if I can end this. I think I will end with this. Yes, I'm going to end with this example. Oh no, but don't look at the answers. No, I got rid of it. Oh no. Dang. All right, there we go. Is that the one? Yeah. All right, let's do that one. So that should, 10 minutes should be good. And some of you might have seen these other instructions that avoid conditionals. Those are in the extra slides. If you're interested, take a look at those.
They also help obfuscate your code too when other people are trying to deconstruct the assembly.
Not if you know what those there's other ways to obfuscate. All right. So this moves 0 into RAX. So this is likely what's going to be returned. And then it does a jump to L5, which tests this condition. So this is likely the condition that's here in the while loop. And we just talked about earlier, when you do this test quad of RDI to itself, the only way this is going to be equal to 0 is if x is equal to 0. So that's why the branch is for not equal. So that's why this is while x. And you could have done while x is not equal to 0 as your condition. The next one is, so the branch here goes to L6. You do an XOR quad of x, which is an RDI, into RAX. So assuming that this is val is equal to 0, because this is moving a 0 into RAX, this is taking val and XORing it with x. And then you do a shift right quad of RDI. So this is shifting x by 1 position to the right. And then this loop is going to execute until x is 0. And then after x is 0, this is what happens in the fall through. You do an AND quad of $1, so this is hex 1, into RAX, which is your value. So this is what gets returned, because the RAX that's left is val and with hex 1. So it's what?
One, the end result, like you had to bring it on the screen, but just one.
It's either 0 or 1.
Oh, okay.
Well, it depends. Yeah, it's a 0 or 1 depending on the val.
Isn't SHR
So with the big
two operand?
Yeah, so we just talked about that. When it's missing that operand, you just assume it's 1 bit.
It's a very,
Yeah.
very obscure way of saying this. It's a really obscure way of saying is x even or odd?
No, that most significant bit is the most significant bit. Yeah, it's checking the sign bit or something. It's doing something silly, but like this is just for example. So yeah, all right. So today we're gonna continue with control flow. We did for loops. We did if then else's. We did while loops, and we saw how these conditional branches are used to implement those loops. The next control structure that we're going to look at are the switch statements. And so you recall a switch statement is basically a test. You're basically testing, so say you've got a variable x, which is your input variable. You are testing whether x is any one of these cases, and then based on its value, you will execute the code that's associated with it. Right? And then within the case statement, if you see a break, that this will pull you out of the switch statement. If you don't see the break, then this case, for example, will just fall through to the next one, and then we'll break on case 103's break. And then for switch statements, if you don't match any of these labels, then you execute the default label, which is down here at the bottom. All right. Does everyone recall switch statements? It's sort of unique to C. I don't know many other languages that do this kind of thing. Okay, so you have some implementation options. From last class, where we had these compares followed by conditional jumps, one way you could implement this is just with a series of conditionals, right? Compare quad $100, and then $101, $102, etc. What's the issue with that if you wanted to implement it that way?
It's comparing it a lot, and it's doing a lot of operations.
Yeah, that's basically a linear operation on the number of case statements you have in your switch statement. That is not optimal at all. And then you know, order n on this kind of thing is something you want to avoid. So this is good only if you have a very small number of of case labels. But if you have a lot of cases, then you don't want to use this method at all. So what method do they use? Well, that's what this is going to talk about. I'm going to introduce this notion of a jump table. And a jump table is an array of pointers to code. And each of these pointers is going to point to a destination in that case label. So, for example, this is the simplest one. I have a switch on a variable x, and I have cases from basically 0 to 5, and then stuff at the default. So what I'm going to do is I'm going to create this switch table, and I'll locate it at .l3 as the sort of an address. And I'm going to say, you know what? I'm going to, for each one of these cases, give you an entry in this table. This is going to be an array. And then I'm going to, based on your label, I'm going to index into this array and then jump to that location. Does everyone see that trick? Yeah.
So doesn't that assume that your cases are actually linearly distributed in some way?
Yeah, assumes this is the nicest thing you could give this implementation, right? There's a small range, and it starts at 0. So I can use this x, and my jump table is only going to be like 6 entries long. That's great. That's like ideal. But here's the key. This is an order 1 operation, right? I take the variable x, and I use it as, well, the first thing I have to do is I have to check to see if it's greater than 5. If it's greater than 5, then I have to have an if statement that says just jump around this whole thing and go to the default. But if it's in between 0 and 5, then I will use that label directly as an index to access this array of function pointers, and then I'll jump directly to that location. Yeah.
So what if you do something like that's not as linearly distributed, where you're dealing with like, okay, if this value is, you know, x squared or x cubed or something, doesn't that mean your table has to be as big as that distribution?
Yeah, as big as the range. What happens if you have one case is 1 and then a case that's 2 million and then a default? What are you going to have, a table of 2 million function pointers? Here's where the compiler, like, let's put it, the compiler has to figure this out, right? So it might implement part of your switch statement using if then else's and jump equals, and then it might use a switch table or a jump table for the rest. But it's only going to work if the range of labels is small, because then you have a small jump table. That's the key. Yeah.
Would you ever really see like a case 2 million or something?
No, you wouldn't. But it would be funny to try and send that to the compiler and see what it did. In fact, you can all write this code, change the labels, and see what kind of implementation you get, and see how good that compiler is at generating code. This is a classic space-time trade-off. So you guys are looking at in your algorithms class. If I throw more space at it, I get less time in execution, and vice versa. So, and of course, we got gigs of memory. So yeah, why not? Why not create a huge jump table and then just do this as an index into it? All right, so let's see one of these things. So here is our example revisited, case 100 through 106, and they don't start at 0. That sucks. What am I going to put a table that's got a whole bunch of default cases for the first 100 entries? Probably not. The money part of this switch table is right here, starting from 100 to 106. So I'm going to have to monkey around with this x in order to use it as an index into a jump table that will give me the right jump. And that's what we're going to look at because that's what the compiler will generate. And this is the core of that switch table level in the meta-CTF. So in fact, I would suggest after this lecture, just go and try that level because it's basically this, decoding one of these. And you're going to try and figure out the case that leads you to the print good job thing. So that's basically the core of that level. Okay, so I am going to walk through this switch statement because when you compile this switch statement, you get this assembly code. So what I'll walk through is how this works. The first thing that happens is we saw earlier we've been passing the parameter x in RDI, that register. So the first thing that happens is you're going to load x minus 100 into RAX. You're going to subtract 100 off of x, the first thing through here. So what does that do? It offsets your label so that the what's left over can be used to index into a switch table. You're offsetting it at, you're clearing out the first 100 of it. Yeah.
Doesn't that actually change your result though?
Well, your result is going to stay, this is your index in RAX. Your result can still be an X, or in RDI. So if you note, all of the operations are using RDI sort of as part of this. So implicitly throughout this code, you'll see that the result is stored in RDI and then accumulated onto RAX. RAX is used initially as the index, but then it gets remapped later on to hold the result. So that's that's looking ahead a little bit, but yeah, that's what's going on. So the first thing we want this jump table to start at an index of 0 rather than an index. Well, we want it so that the index goes from 0 to 6 rather than from 0 to 106. So that's why we're offsetting the jump target by 100 so that we can make this case 100. We can make this pointer correspond to the x minus 100, which is basically the 0, the origin for the jump table. Okay, after we subtract 100 off of x, then anything that's above 6, so the range of this switch statement goes from 100 to 106, so the range is basically 6, and everything above 6 goes to the default, right? So that's what this is. This is your default statement right here. Jump above 6. After you've offset by 100, anything above 6 is going to go to L8. And L8 is move 0 into EAX and return, which is the default code. Okay? So one of the things is that if the number is between 0 and 100, as soon as you do this LEA quad, you get that wraparound. You get this large sort of negative number, which ends up being in this unsigned compare. It's going to give you the default condition. Then what you're going to do is you're going to take what's left over. This was the index in RAX. You're going to use what's that index as an offset into this jump table. Now this jump table has a bunch of pointers to code, and each one of those pointers is 8 bytes. So that's why this is 8 times the index. And then you're going to add it to .L4. .L4 is sort of the base of the address of this jump table. And then you're going to say, I'm going to do an indirect jump. So what I'm going to do is I'm going to calculate this address. And then I'm going to go into that memory location and jump to the address that's there. So that will actually index this and jump to the various code locations that you have in the switch statement. Yeah.
Just walk through it with an example at like x is like 102.
So x is 102. I subtract 100 off of that. So now RAX is 2.
All right.
I compare 2 to 6. And 2 is not going to be above 6. So then it's going to go to this. And then it's going to say multiply 2 by 8. Add that to .L4, so you start at L4, and then 2 times 8 will put you, this is the 0, the 1, the 2, it will put you here at L5, and then jump to it. And if I jump to L5, it's down here. And that's where your case 102 is.
It doesn't have a return.
Yeah. You see that trick? Yeah, that's pretty subtle. And you note that some of these case labels, or some of these destinations, will show up multiple times. So for example, case 104 and 106 goes to multiplying the result by itself, so squaring the result. You will see, where is this? So this is .L7 and .L7. This is 104 and 106, where you're basically multiplying result by itself and returning. The other thing is, you know that you see that case 101 doesn't appear here, but if you have 101, it should go to the default. And so if you look, the very first where 101 should be has a pointer to L8, which is your default code. All right. So again, these labels are pointing to code locations down here that will then implement these pieces of code. So the red arrow is implementing, taking the result and multiplying it by 13, and it's doing that LEA quad trick again. It's doing it's calculating 3x, and then it's taking that, multiplying it by 4, and then adding x again. So that's like 12x plus another x, which is 13x, and then it's returning. So this is the code that implements that, and because this is the first case statement, after you offset by 100, you end up putting .L3 in that location. Okay. Any other questions? So here's where I'm going to ask you to reverse engineer this. Practice problem 330, and then if you can do this, go ahead and do the binary after class, because the binary is exactly find the switch, find the integer that will get you to the code location that will print good job.
This is automatically optimizing the case if it's way outside the range. It just jumps immediately to default.
Yes, that jump above. Anything that's crazy gets covered by that jump above. Yeah, that's correct. Sort of most of it. So let's walk through this. Because you're offsetting the index by adding 1 to it, the range is really starting at -1. And that puts the switch table up to 0. And then you're going to compare to see if what's left over is above 8. So that means the top of that range is 7. And then anything after you add 1, anything above 8 is going to go to the default case. All right. So the default goes to L2. And then you can start mapping the indices starting from -1. So -1 gets the code at L9. 0 gets L5, as well as down here, 7 gets L5. 1 gets L6. 2 and 4 get L7, etc. So you go all the way down. And then you don't have to put case 3 and 6 there. I just did that because just to make it clear. Yeah, but yeah, you don't need that.
So the case 3 and 6 could be in there, but it doesn't have to be.
Yeah, they'll be equivalent. Yeah.
Yeah.
You can omit it. Yeah.
So maybe a stupid question, but like, if you jump into case 1 and it doesn't have a break after it, does it go and check if it's the next case?
Nope.
Or it just
Falls right through.
executing all the code below?
Yep.
Oh, okay.
It keeps on executing. Yeah, you won't see an if then else after here that checks for the case. Yeah. So you have to organize your case statements, and there's a reason why the switch statement has this semantic, because it knows underneath how it's going to implement it, and so that's why the break you can definitely implement, But then checking for other cases beyond that doesn't happen. This is a one-shot thing in terms of checking cases.
Puts you in a spot that doesn't.
Yeah, pretty much, yeah. And that's what the compiler wants to do. It doesn't want to have to add checks to go somewhere else, yeah.
That's a lot more.
So if the starting range was 2, let's say the IQ was 2, then it would be like start range would be -2,
Yep.
the top range would be 6.
6, yep.
Okay.
So, and this will be for your binary, if you see like 15,000 is subtracted, well then you know that the case statement starts at 15,000. That's your 0. And then you can count upwards, and then you say, well, I know that label. You can reverse engineer .L6, and you say, hey, that puts the good job string on the stack, and then calls puts. Then you're like, well, if it's 15,000, maybe 15,001, 15,002, and then you're like, that's the integer. That's the password. So that's your level.
Oh.
That's what I'm suggesting you do right after class, because now that it's fresh, you can actually just solve that just like that. All right. Questions before I move on? All right. So yeah, I encourage you again to do your Meta CTF levels. They're coming fast. Basically, in fact, this chapter is the reason why I started Meta CTF, and so that's why most of the levels are for this chapter. And that's why there's no programming assignment for this chapter. All the Meta CTF levels are covering this. All right.
I mean, that's why we have this extended period of time.
With no other assignment, it's basically, you should be just doing all those levels.
Also, that's what you suggested, better to focus on the Meta CTF and then like probably a week before the assignment to focus on the assignment.
In fact, the website was wrong. There was no A3, so
There's no
I updated the website. So here, actually, I should
I'm
stop
making
this.
my mind over it.